Okay, now we've arrived to the last parameter that we're going to talk about, and that is the standard deviation, or variance, right? Because the variance is just the square of the standard deviation, so it'll be sigma squared. Okay, all right, so the objectives here are to find the critical values for a chi-square distribution, which is a new distribution that we're going to talk about. Construct and interpret confidence intervals for the population variance, or standard deviation. Just like all the other parameters, like the proportion or the mean, anytime we take a sample from the population and we calculate either the proportion or the mean, it should vary from sample to sample. And it's just the same for standard deviation, right? If we calculate the standard deviation for a different sample, from one sample to another sample from the same population, you don't expect it to be the same. It will vary from sample to sample. The thing about standard deviations is that when we calculate them, they're always going to be a positive number, right? And for normal distributions, we know that it goes from negative infinity to positive infinity. So it doesn't really make sense for a standard deviation to have a probability that it's a negative number. So the probability of a standard deviation being less than 0 has to be 0, right? There can't be a possibility that the standard deviation is a negative number. Okay, so that's why we're going to introduce this new distribution here, and that's called the chi-square distribution. And this is the distribution chi-squared. This is a Greek letter chi. It looks like an X, and there's a little 2 at the top. That means chi-squared. I wouldn't worry too much about that too. The purposes of that is a little bit beyond the scope of this course. Now, what we really want to focus on this sample standard deviation, this S here. What we're saying here when we're looking at this distribution is that, well, you see how it starts at 0, right? And there's nothing to the left of this 0, right? It's all in the right-hand side of 0. So it kind of looks like a normal distribution, but it's not symmetrical. That's the first thing to notice. It's not symmetrical. It goes from 0 all the way to positive infinity. Now, there is some sort of peak where the standard deviation should be, right? But then again, there is a probability that's any value between 0 and infinity. Okay, of course, as you go towards infinity, that probability becomes very, very small, right? But the most likely value of your standard deviation is somewhere around this region, I would say. All right, so what are the characteristics of the chi-square distribution? Okay, well, the first thing is that it's not symmetric. That's the first thing that you notice. Now, the shape of the chi-square distribution depends on, again, the degrees of freedom, just like the student's t distribution. Okay, so the degrees of freedom is related to the sample size. So the larger the sample size, this chi-square distribution starts to look a little bit different. Okay, now as the degrees of freedom increases, what we start to see is that this chi-square distribution becomes nearly symmetrical. Okay, so as you can see from this graph here, the chi-square with 30 degrees of freedom is this purple one, right? And that does start to look like it's normally distributed. Okay, and everything else is a little bit further to the left. The peak is a little bit further to the left. Okay, the one weird one is where we have degrees of freedom 2. It doesn't actually start at 0 like all the other ones. Everyone else starts from 0, 0. But the one with the degrees of freedom 2 is kind of a weird one. And then again, the values of chi-squared are all non-negative, meaning that they're greater than or equal to 0. So just like for the z distribution and the t distribution, we need to find critical values. Okay, and for the critical values for a chi-squared distribution, they're found in this fashion. Okay, now we have this horizontal axis here. We also have a vertical axis, as you saw on the previous page. Again, this starts at 0 there. And now the two critical values that we're looking for are these two. Now the subscripts there just refer to the area to the right of those values. So what I like to call these instead are chi-squared left, chi-squared right. Therefore, this one's chi-squared left, this one's chi-squared right. But technically, if you're using the correct notation, you would just use the area to the right. So that's 1 minus alpha over 2, and then this one would be alpha over 2. All right, in order to calculate these critical values, on your TI calculator, you need a special program because natively on your calculator, you don't actually have a way to calculate these numbers. Okay, but I'm going to show you how to calculate these with a program that you can just look up on a web browser. Okay, so for example 1, it says find the chi-squared values that correspond to a 95% confidence level and 18 degrees of freedom. So just like the other problems, you want to come up with a picture. Okay, you want to have a vertical axis and a horizontal axis. These both intersect at the point 0, 0. And let's go ahead and draw it. So it looks like that, and it has a long tail that goes on forever. But it does start at 0. Okay. We want to make up the middle 95%. Okay, so there is a cutoff right here. We're going to call that chi-squared left. And there's one on the right side, chi-squared right. And let's go ahead and partition that. The middle portion is going to be 95%. And because we are saying that this is the confidence level, this is the middle portion, what's left over? Well, 5%, right? And half of 5% is 2.5%. So each one of these regions here is 0.025, 0.025. Now they don't look very similar, but the areas are exactly the same. Okay, the shapes might look different, but the areas are the same. Okay, let's go ahead and calculate this using the web page I found. Okay, so I found this web page called GraphPad. I'll link it down in the description. And it has all sorts of different calculators. All right, for this particular problem, we're going to be in the menu for statistical distributions and interpreting p-values. Okay, and we're going to go ahead and choose calculate ZTF or chi-squared. So we're really interested in chi-squared, okay, from a probability. So let's go ahead and continue. Now again, you have the options to find all the z-scores, t-scores. We haven't talked about f yet, but that'll come at some point. And then chi-squared. Okay. Now, what they mean by probability, they decided, I played around with this to figure it out. They decided to use the right area. Okay. So if I'm going with the 2.5% and the degrees of freedom, they said what? 18. And let's go ahead and compute the chi-squared for that. I get 31.526. The area to the right of that left partition is 0.95 plus 0.025, which is 0.975. Okay, and again, same degrees of freedom, 18. Compute that. And we get 8.231. All right, let's do another one. Same idea. This is going to be chi-squared left, chi-squared right. Okay, we're looking for an 80% confidence level and the sample size of 30. Well, if the sample size is 30, that tells us that the degrees of freedom are n minus 1, which in this case is 30 minus 1, 29. All right, let's go ahead and draw a picture again. That's 0. Again, we're looking for the middle 80%, so let's just go ahead and cut this down. This middle portion is 0.80, and the remaining portions have to add up to what? 0.2, and that means that there's 0.1 in each tail. This is 0.10, 0.10. All three parts have to add up to be 1. Okay, this is chi-squared left. This one's chi-squared right. So let's start with the right one. The area to the right of this is, well, it's 0.10. Okay, so let's go over to our calculator. 0.10. Degrees of freedom, they said it's 29. Let's compute chi-squared. And we should get 39.088. Let's do it for the left-hand side. Now for the left-hand side, the area to the right of that is 0.80 plus 0.10, which is 0.90. Again, same degrees of freedom, 29. And we can compute. And we get 19.75. 7677. Okay, now that we know how to calculate critical values for chi-square distributions, then we can start talking about coming up with the confidence interval. But first, let's talk about the requirements. Okay, we have the typical requirement of our data has to be obtained by using simple random sampling, but we have a more strict requirement that the population must be normal. Okay, we can't use any of that n greater than 30 business here. Now, this is a little bit different than for the proportions and the mean, because we're not taking a point estimate and adding and subtracting a value. Okay, so if we're looking for the confidence interval for, let's say, the variance first, sigma squared, that's some lower bound and some upper bound. And this here, again, this is chi-squared. This is actually the right side, and this is the left side. Okay, you might be asking, well, why is the right one on the left and the left one on the right? Well, the right value is a larger number, and it's in the denominator, so that makes this fraction smaller. And the left critical value is a smaller number, which makes this fraction bigger. Okay, so mathematically, it is in the right place. Now again, the relationship between variance and standard deviation is that one is the square root of the other. So if we're looking for the standard deviation, all we have to do is put square roots over each one of these quantities. Again, if you have a TI calculator, and if you were in my class, I would actually give you this program, Math 200B. Okay, and you would follow these directions to come up with the interval. But we're going to use the web browser resource. All right, so let's see how we actually calculate this confidence interval. Example 3. One way to measure risk of a stock is through the standard deviation rate of return. Okay. The following data represent the weekly rate of returns in percentages of Microsoft for 15 randomly selected weeks. Compute the 90% confidence interval for the risk of Microsoft stock. Okay, so what are they asking for? They're asking us to compute the 90% confidence interval of the risk. Well, what is the risk? Well, they're saying that the risk is measured through the standard deviation. Okay, it just tells you how spread out these values are. Okay, so if you have rates of return that are very spread out, very volatile, you say it's more risky. And if they weren't that volatile, then you'd say that's less risky. All right, now they do say that the population is assumed to be normal. Okay, so it does meet that requirement. Now, if you were to run this to your calculator, maybe put this under L1, we would return with a sample standard deviation of this, rounded to 3 decimal places. Now, in order to calculate the, again, confidence interval for the risk, which is the standard deviation in our case, then let's start off with the confidence interval formula. We have the standard deviation is bounded between square root of n minus 1 s squared over chi squared right. And on the right hand side we have the same thing, n minus 1 s squared, but instead of chi squared right we have chi squared left. All right, let's go ahead and catalog all those values. So we need an n, we need that s, we need chi squared left and chi squared right. So we need 4 values in order to calculate this. Well, I did say if you run this through one of our stats, you get a sample standard deviation of 4.697. So that was just given. Otherwise, you would just have to do that on your own. Okay. The sample size, well, does it tell us how many? Well, it does. It tells us that there's 15. Now, if they didn't actually tell us how many there were, we would just have to count all the data values, right? So there are 15 here. Chi squared left and chi squared right. Well, in order to come up with those values, let's go ahead and draw a picture and then just use that web resource. All right, so we have 2 partitions here, chi squared left, chi squared right. we're looking for a 90% confidence level, so that middle portion is 0.90. That means these two tails have to be what? Well, they have to be 5% each. All right, let's go ahead and switch over to the calculator. All right, let's do the left one first. So the left one should be 0.90 plus an additional 0.05, which is 0.95. Degrees of freedom is your sample size minus 1, which in this case is 15 minus 1, or 14. Let's compute that. Okay. We get 6.571. All right, let's do that same thing for the right chi-squared critical value. In this case, there is 5% in that tail. Degrees of freedom being 14 again. Compute that, and we get 23.685. Okay. So now it's just a simple matter of correctly plugging this into your calculator. All right, we need a square root. N minus 1 is 15 minus 1. I'll do this in multiple steps. S squared is 4.697 quantity squared. Denominator here. Now, you're not going to square this number. It's already technically squared. Okay, that's just more. Think of that as just more of a notation. Okay, so we're just putting in 23.685. You don't have to square that at all. Just think of that chi-squared being a notation. It makes your life a little easier if you think of it that way. Over here we have 15 minus 1, same standard deviation. And then the lower bound here is 6.571. All right. Let's go ahead and put this in the calculator. I want to show you how to actually do this all in one shot. So you have the square root of 15 minus 1, which is just 14, times 4.697. Don't forget to square that. Divided by 23.685. All right, I get 3.611 for my lower bound. Now for my upper bound, instead of having to retype this, I can just do second enter, and it recalls the previous calculation I did. And all I really have to do is change the critical value there. I'm going to change that from 23. We'll delete that. To 6.571. 6.571. Enter. And we get 6.856. And the interpretation here is that we are 90% confident that the population standard deviation of weekly rates of return is between 3.611 and 6.856. And they did say to us that these were measured in percent. So these are percentages. So now that we found the confidence interval for the standard deviation here, now that same website also gives you a way to come up with this interval just with a few inputs. Let's try that out. So on this page, if you just go to where it says continuous data, you'll see that it says CI of the mean difference ratio, SD. The CI refers to confidence intervals. So let's go ahead and click on that. And then right here, we're going to choose the calculator that we're interested in. We're looking for the confidence interval for a standard deviation. There's different ways that you can actually enter your data. You can either put in actual data, but we're going to be using SD and N, which is the standard deviation and the sample size. Again, in our example, the standard deviation is 4.697. Sample size was 15. And this should be enough information for them to determine the confidence interval. So let's go ahead and calculate now. Now the only thing about this calculator is that they only give you confidence intervals for 3 different kinds: 90%, 95%, and 99%. So if you had any other percentage, this wouldn't work out. You would have to do it the way that we just did it. Okay. So in our case, we wanted a 90% confidence interval, and that's what we have right here. All right, let's do another example. Example 4. When playing disc golf, the weight of disc has a huge effect on the disc performance. A simple random sample of 12 discs is drawn from a population that is known to be normally distributed. That's good to know. A sample standard deviation S is determined to be 1.97. Okay. Saying construct a 99% confidence interval for the population variance, okay, of the disc weight. Okay, so let's go ahead and just set ourselves up. We're looking for a confidence interval for a variance, so that's sigma squared, right? Lower bound and upper bound. Now, if we were to use that calculator like we did before, that calculator only gives you confidence intervals for standard deviations, okay? Now, what we can do is just calculate for the standard deviation, and what we would have to do for those lower bounds is just square each side. Okay, so that would actually work. Okay, so let's go ahead and catalog what we have. We need to know what the sample size is and the sample standard deviation. Sample size is 12 discs, and they tell us that the sample standard deviation is 1.97 grams. 1.97 grams. All right, so let's go ahead and calculate the confidence interval for the standard deviation first using the calculator. Okay, now using the exact same calculator from the previous example, which was for the confidence interval for our standard deviation, we're going to go ahead and do this for this problem too. Okay, the standard deviation in our case is 1.97, sample size 12. Let's go ahead and calculate now. And in our case, we're looking for a 99% confidence interval, correct? So that means we are looking at this interval here. Okay, now that gives you the lower bound and the upper bound for the standard deviation. All right, so let's go ahead and copy those over. 1.2631, make sure that we square that value, and also 4.0496, also squared. That gets us, let's go ahead and do 3 decimal places, 1.595 and 16.399. So we say we are 99% confident that the population variance of disc weights lies between 1.595 and 16.399. Now the units associated with this are standard deviation is the same units as your original data. The original data was in grams, right? And then since it's a variance, it has to be grams squared. So grams squared. Kind of a weird unit. That's why the preferred measure of spread is standard deviation, which is the exact same units as your original data.